section we're going to cover in our trigonometry or video is called DeMoivre's Theorem. DeMoivre's Theorem. Okay, so we're going to talk about how we can express this complex number a plus bi using trigonometry. The x-axis, or the horizontal axis, is going to have the real numbers. And the vertical axis, well, that's going to be the imaginary. So a is the real part and bi is imaginary. We go at a on the reals and b on the imaginary. That puts us right here. And the question is, how can we relate this or express this point right here using trigonometry? Well, here's our right triangle. And I guess a should be just ever so little bit more to the right. A should be a little bit more to the right. So this is a point a plus bi. Now, this horizontal distance, well, that's a, and this vertical distance, that's b. Well, it turns out that the tangent of theta is opposite over adjacent. Now, how long is this? How long is, I'll call it r. How long is r? Well, Pythagoras would say that a squared plus b squared is r squared. If I don't write r squared, that is, if I take the square root of r squared, I'll get r. I have to take the square root of the right side. Okay. Now, what is, for example, the sine of theta? The sine of theta is opposite over hypotenuse. I have every right to put the hypotenuse up there, or the denominator up there. The sine of theta is adjacent, which is a, over r. I have every right to put the r up there. So here it goes. A plus bi. Well, a is r cosine of theta, plus b is r sine theta times r. Now, all I'll say is that each term has an r. I can factor it out. So it's r times cosine of theta plus sine theta times I. I'll just put the I in front. Any complex number can be written this way, where the tangent of theta is b over a, and r is a squared plus b squared square root. Any complex number can be written as r cosine theta plus I sine theta. And I have to tell you how you get to theta. Well, the tangent of theta is b over a. That is, the tan inverse of b over a is theta. And I have to tell you how to get r, and I did. Okay, that's important. Okay, I'm going to give you some complex numbers. I'm going to ask you to write it using DeMoivre's theorem, which is the one that you see in front of you right now. And that'll be it. Okay, so suppose I give you 1 plus I, which of course is 1 plus 1i. So remember, it's r times cosine of theta plus I times sine of theta. I need to find r, and I need to find theta. Okay, well, let's find r first. 1, well, that's b. So r is equal to a squared plus b squared square root. R is 1 squared plus 1 squared square root, which is 1 plus 1 square root, which is the square root of 2. So now I have r. It's the square root of 2. Now I have to find the cosine of theta. Now, you can just draw this diagram. You can draw the diagram to real and imaginary. Go 1 to the right, go up 1. That's right here. Well, this here is square root of 2. I mean, we should have known that without even doing this mess here. And I know that angle. It's 45 degrees. 1 square root of 2. Okay, so what's the cosine of 45 degrees? It's adjacent over hypotenuse. 1 over square root of 2 plus I times, the sine is opposite over hypotenuse. 1 over square root of 2. Now, coincidentally, when you multiply, you get 1 plus okay, excuse me. We know the angle. It's 45 degrees or pi over 4. So that's what we write. Cosine of pi over 4 plus I times sine pi over 4, and the problem is done. The problem is done. Okay, let's try another one. Okay, let's try to keep the formula on the bottom so we have it when we need it. The next problem is as follows. Negative 1 plus square root of 3i. Negative 1 plus square root of 3 times I. And what we want to do is write this in r times cosine theta plus I sine theta form. That is, we want to replace r with something and theta. Everything else stays the same. Okay? So we have the rails and we have the imaginary axis. The rail is negative 1. Imaginary is positive square root of 3. That brings me right here. That tells me this here is negative 1 and this here is square root of 3. But this is a special right triangle. We know that r is 2. Okay, r is 2. R is 2. And you know what? We even know this angle. We know the reference angle. It's a 30, 60, 90 triangle where opposite square root is 3 is 60 degrees. So this angle is 120 degrees, or 180 divided by 3, that's 60, 2 times that. So there's the answer. Cosine 2 pi over 3 plus I times sine 2 pi over 3. You wanted to find r, you wanted to find theta. Notice we don't really deal with, if we recognize a triangle, with tangent and theta is b over a, nor do we have to do a squared plus b squared. We recognized it. I mean, negative 1 squared plus square root of 3 squared. Well, that's going to be r squared. Well, actually, r is the square root of that. Negative 1 squared is 1. Square root of 3 squared is 3. This here is square root of 4, or 2. R is 2. But we already knew that because it's a special right triangle. When it's a special one, we deal with it that way. You're like, oh, okay. I recognize all those answers. I know the angle, and I know their hypotenuse. R is the hypotenuse, or the radius. Suppose you had 3 plus 4i. So that's in quadrant 1 because the real part is positive and the imaginary part is positive. 3 to the right and 4 up. This is 3, this is 4. You should know that that's 5. You should know that's 5. 3, 4, 5. The special right triangle. So R is 5. Okay, so R is 5. Now, what is the angle? Well, we know that the tangent of the angle is B over A, 4 over 3. So then the angle is the tan inverse of 4/3. Take our calculator and we find the tan inverse of 4 divided by 3. Make sure you're in degrees. Actually, so I get 53 degrees. But actually, we really do want to be in radians. Instructions like these in radians. So let me change my mode. Okay. The tan inverse of 4 divided by 3 is 0.9273 radians. Plus I times the sine of 0.9273. Okay, why did I have to use this rule? Because I don't recognize that angle. I don't recognize that angle. If I recognize the angle, I would be done. There are other answers you could have said. Now, since this is an approximation, you could have said theta is this angle, and you could have written this is 5 times the cosine of the tan inverse of 4/3 plus I times the sine of the angle, which is, to save space, t to the minus 1 meaning tangent of 4/3. Okay, that's another way of writing. That's exact. What I have next to the last line, this line right here, is an approximation. Okay. Now, let's look at what happens when we multiply two numbers or two expressions in the form that we're talking about. Let me just say something. When you have r cosine theta plus I sine theta, r is r. Some people write C I S theta. C I S angle theta. So when I say you want to write it in CIS theta form, you'll know what I mean, or I times CIS theta form. What happens if you multiply two of these? The only thing that changes from one to another is R or the angle, or both. There's one, and I'm going to multiply by another one. They are 2 times cosine of theta 2 plus I times sine theta 2. Oh, we're multiplying 4 things. 1, 2, 3, 4. I feel like multiplying the first and the third Now I'm going to multiply this times that. Well, and I'll use the distributive rule. I'll get cosine theta 1 times cosine theta 2. And then I'll do those two. Remember, positive I times positive I is positive I squared, which is minus. Minus sine theta 1, sine theta 2. That's the real part. Those are big brackets. Now let me add on the imaginary. I then multiply cosine theta 1 times I theta 2. I sine theta 2. Well, the I is going to factor out. You see that. You have sine theta 1 times sine theta 2. Well, do I believe that? No, I do not. Like I said, cosine theta 1 times sine theta 2. So this should have been cosine. Sorry. Hope you caught that. You get some more i's. You multiply these two. I times, and I factored out the I, plus sine theta 1 times sine theta 2. So we get R1, R2. Now, this here is cosine theta 1 plus theta 2. And amazingly enough, what's in the second bracket is sine theta 1 plus theta 2. Go back and look at your sum rules, you'll see it. Okay, so basically, when you multiply two of these, it's very smooth. You multiply the two r's, and then you take the cosine of the sum of the angles plus I times sine of the sine of the angles, of the sum of the angles. So, for example, somebody asks you what is 3 times cosine of 20 degrees plus I times the sine of 20 degrees, multiply that by 4 times the cosine of 10 degrees plus I times the sine of 10 degrees. Well, what you're going to get is you multiply the r's, 3 times 4 is 10, and then you add the angles. 20 plus 10. 20 plus 10 is 30. And then you play the same game with the signs. You add the angles. And there's the answer in CIS form. If you want to write an exact answer, that is, excuse me, you don't want trigonometry. Well, then you say the cosine of 30. Well, what's the cosine of 30 degrees? Well, here, 30, and so this is 1, 2, square root of 3. The cosine of 30 is square root of 3 over 2, plus the sine of 30 is 1 over 2. The 2's in the bottom kill out the 12 in the front. It goes into the 12 in the front 6 times. So you get 6 times the square root of 3 plus 1. Now, you won't derive this one, but it's exactly done the same way. Very similar to what we just did with product. But what if you divide two such things? What if you divide two of these such things? What if you divided R1 cosine theta 1 plus I times sine theta 1? You divide this by another one. We'll call it R2 cosine theta 2 plus I sine theta 2. It turns out going to be R1 over R2 CIS of theta 1 plus theta 2. Actually minus. You get cosine of theta 1 minus theta 2 plus I times sine of theta 1 minus theta 2. That's what happens when you divide. So if you were given this, you're asked to do 2 times cosine of pi over 4 plus I times sine pi over 4. You're being asked to multiply this by 5 times cosine of pi over 3 plus I times the sine of pi over 3. Well, 2 times 5 is 10 times the cosine of pi over 4 plus pi over 3. Pi over 4 and pi over 3. If you prefer, you can look here and there. Plus I times the sine of the same angle. Pi over 4 plus pi over 3. Okay, now you should really add these angles. What is pi over 4 plus pi over 3? Well, the LCM is 12. If I multiply this by 3 over 3, I'll get 3 pi over 12. And if I multiply this by 4 over 4, I'll be adding 4 pi's over 12, which is 7 pi over 12. That is, this is 10 times the cosine of 7 pi over 12 plus I times the sine of 7 pi over 12. These two angles should always be the same. These two angles should always be the same. They should always be the same. So now, the next statement is really what's called DeMoivre's theorem. What if you have one of these objects? You have r times cosine theta plus I sine theta, and you raise the whole thing theta to the n power. What if n was 2? If you multiply this by itself 2 times, r times cosine theta plus I sine theta. What if you did that? Well, the rule says you multiply r times r, and then you add the angles. Theta plus theta. 2 theta plus I sine 2 theta. Oh, let us just call this, let's call this z, okay? So z squared. Well, what if you wanted to cube it? Well, isn't z cubed the same as z squared times z? And z squared we have is r squared cosine 2 theta plus I times sine 2 theta times z, which is r cosine theta plus I sine theta. R squared times r is r cubed, and you add the angles. 2 theta plus 1 theta is 3 of them. I sine 3 theta. DeMoivre's theorem states that if you have v to the nth power, you'll get r to the n cosine n theta plus I times sine n theta. Is the record when it was 3, when n was 3, it was 3 theta. When n was 2, it was 2 theta. When n is, when the power is n, you get n theta. Okay, this here is exactly DeMoivre's theorem. So now, what if you were asked to do the following problem? So, DeMoivre's theorem is nice and beautiful and all that, but can we apply it? The answer is yes. Suppose you wanted to calculate 1/2 plus 1/2 I to the 10th power. To the 10th power. Suppose you wanted that. Okay, well, can we write 1/2 plus 1/2 I in CIS form? The answer is yes. We can write any A plus BI in CIS form. I don't know why I did that. So now, let's go to their real imaginary plane. We have the reals, we have the imaginaries, and we go out 1/2. We go 1/2 to the right, and we go 1/2 up. Now, this should look like a triangle that we're somewhat familiar with, where these two are the same, and that's square root of 2. Well, if somebody divides all the sides by 2, then we know the hypotenuse. It's square root of 2 over 2. Okay. Or you can use the Pythagorean theorem, which you don't want to do. 1/2 squared plus 1/2 squared. The square root of that is off. Well, 1/2 squared is 1/4 plus another 1/4. The square root of that. 1/4 plus 1/4 is 2/4. I do not know the square root of the top, but I do know the square root of the bottom. Square root of the bottom is 2. So I got it. Or I just think 1 square root of 2, and I divide all 3 sides by 2. Why? Because that's what they did to those ones. They divided it by 2. And nonetheless, I now have the hypotenuse. I have R. So this is equal to R times the cosine of theta. Well, I know this theta. It's 45 degrees. Why? Was the tangent of theta is opposite over adjacent, which is 1. That's enough for me. Theta is pi over 4, 45 degrees. So it's the cosine of pi over 4 plus I times the sine of pi over 4. Okay. So let me get rid of this, please. So when you look at the top line, the second line, to get the top line, we have to raise it to the 10th power. We need to raise this to the 10th power for it to equal that. But this is the same as that. So 1/2 plus 1/2 I. This is the same as the square root of 2 over 2 times cosine pi over 4 plus I times sine pi over 4. That we know. We know these are equal. I raise the left side to the 10th power, which gives me exactly what I want to learn. This equals the right side to the 10th power. That is, you have square root of 2 over 2 to the 10th power. And then the angle just gets multiplied by 10. 10 times pi over 4, which for the record is 5 pi over 2. Now, keep in mind that the square root of 2 over 2 is really 1 over the square root of 2. So, raising this to the 10th power is the same as raising this to the 10th power. So you get 1 to the 10th power, which is 1, and the square root of 2 is 2 to the half. When you raise it to the 10th power, well, you multiply the powers. Half times 10. Half of 10 is 5. And 2 to the 5th is 32. So you get 1 over 32. Now, it turns out that the cosine of 5 pi over 2 is 0. And it turns out that the sine of 5 pi over 2, just use a calculator to figure it out, is 1. 1i. So you get 1 over 32 times 0 is 0. And 1 over 32 times 1i, or I, is just 1 over 32i. So you just multiplied this. You found out what this is without multiplying by yourself 10 times. It was a lot easier than to multiply it by itself 10 times. If you were to multiply it by itself 10 times, though, first I would factor out the half. And then you get 1 over 2 to the 10th, which I don't know what that is. And then you would just have to FOIL this out. At least you don't have any fractions. But you don't want to multiply 1 plus I by itself 10 times. Okay, suppose you wanted to know a power of this complex number. If you want powers of complex numbers, you use DeMoivre's theorem. Suppose you wanted to know what 1 minus the square root of 3i to the, I don't know, the 5th power. Suppose you wanted to know that. What is this equal? Well, the whole goal is to write 1 minus square root of 3i in trigonometric form, in CIS form, and then apply DeMoivre's theorem. We have the real axis, we have the imaginary. The real is 1. The real is 1, and our imaginary part is negative square root of 3. So we're out here. We're out here. That is, here is our triangle, and we know that this is 1, and this is negative the square root of 3. So Pythagoras would say, oh, that's 2. Because we recognize this as a 30, 60, 90 degree triangle, where this is 60. 180 divided by 3. Okay? So what's being raised to the 5th power, we now know. It is r times cosine of pi over 3 plus I times sine pi over 3. But I'm concerned about one thing. See, that's not exactly right, because the angle is negative pi over 3. And the cosine of negative pi over 3 is just what I wrote, cosine of pi over 3. But the sine of negative pi over 3, that's going to become negative. That's going to become negative. Sorry about that. In fact, let me even write this bigger. So, in fact, why don't we just say that the angle is 2 pi minus pi over 3. So 2 pi is the same as 6 pi over 3. That way, the denominators are both the same, and we get 5 pi over 3. Why don't we use that angle? So we know it's r times CIS, 5 pi over 3. c cosine 5 pi over 3 plus I times sine 5 pi over 3. The reason I want a plus in the middle is DeMoivre's theorem has a plus in the middle. Okay, now all of this needs to be raised to the 5th power. So then I get 2 to the 5th, which is 32. And then the angles get multiplied by 5. 25 pi over 3. 25 pi over 3 minus I times sine 25 pi over 3. And at that point, you can just use a calculator. Okay, there's a calculation, and you can just type into your calculator. So you get 32. Now, what is the cosine of 25 pi over 3? Well, 25 pi over 3 is, well, 3 goes into 25 8 times plus or 8 pi plus 20 plus pi over 3. Okay, the thing is that 8 pi is a multiple of 2 pi. It's kind of meaningless. In other words, you go 2 pi, 4 pi, 6 pi, 8 pi, and then a third of pi. Or you can just go a third of pi, you get to the same place. That is, this is nothing more than the cosine of pi over 3. So this becomes the cosine of pi over 3 plus I times the sine of, same argument for 25 pi over 3 over here. It's pi over 3. Now the nice thing is, this pi over 3 is 60 degrees, and we know everything about 60 degrees. 60 degrees. 1, 2, square root of 3. The cosine of 60 degrees is a half, and the sine of 60 degrees is the square root of 3 over 2. You can factor out the 2, that is 36 times a half, 32 times a half is 16, plus I times the square root of 3 over 2 times 32. This 2 still goes into the 32 16 times. 16 square root of 3. In fact, what I meant to do was just to factor out the 16. There is your answer. I raised a complex number to the 5th power, and I ate through it. Just ate through it. It wasn't hard at all. And if you think it's hard, fair enough. But it'd be a lot harder to multiply 1 minus the square root of 3i by itself 5 times. Or worse yet, 55 times or 2 million times. And now, there's another type of rule, is what if you want to find the nth root? What if you want to find the nth root? So, suppose you have r cosine theta plus I sine theta, and you want the nth root of this. That is, you want to raise it to the 1 over n power. Well, the power is 1 over n. So you get r is the 1 over n, and the angles get multiplied by 1 over n. Theta times 1 over n is theta over n, plus I times the sine of theta over n. That's what you get. Okay, but the problem is that you can always add 2 pi to the angle. You can always add 2 pi to the angle. That is, you rarely get this cosine of theta plus 2 pi k over n plus I times sine of theta plus pi k over n. That's their nth root. So for example, if you have z is equal to negative 64, and you want to find the sixth root of negative 64. In fact, that's the problem. Find the sixth root of negative 64. Now, I'd like to write negative 64 in CIS form. Negative 64 times CIS. That is cosine of some angle plus I times the sine of an angle. Now, you just have to remember that negative 64 is equal to negative 64 times 1 plus no i's. Is I want to put an angle so the sine of the angle is 0. And that the cosine of the angle is 1. And okay, for example, I want the number in front to be positive. So I want the cosine of the angle to be negative 1. So how about the cosine of pi? The cosine of pi is negative 1, and the sine of pi is 0. Okay, so this is just another way of writing 64, negative 64. This is just another way of writing negative 64. And you'll see in a moment why you want the number in front to be positive. Okay, so using DeMoivre's theorem, let us see what we get. We get that negative 64 all to the 6th power is equal to 64 to the 6th power. Now we can calculate 64 to the 6th power. I think it's 2. Now if I had instead negative 64 to the 6th power, well, I can't calculate that. That's what I'm being asked to calculate. If I knew what negative 64 to the 6th power was, I wouldn't have to do this problem. I would just write down the answer. So I want the number in front to be positive, 64. I want the number in front to be positive. And then what we get is cosine of theta plus 2 pi k divided by 6, because we want the 6th power, plus I times sine of the angle plus multiples of 2 pi over 6. And we know that the 6th root of 64 is 2. What times itself 6 times gives the 64? 2. So it's 2 times the cosine of pi plus 2 pi k over 6 plus I times the sine of pi plus 2 pi k over 6. Now, we just let k be 0 through 5. We let k be 0 through 5. Because if you let k be 6 or 7 or 8, then it's going to be repeated answers. Make sure you see that. Let k be 0 through, you want the 6th root, let it be up to 1 less than 6. Let it be to 5. If k is 0, then one of the 6 roots will be 2 times cosine of pi over 6 plus I I times the sine pi over 6. Pi over 6 is 30 degrees. 30 degrees is 1, 2 square root of 3. The cosine of 30 degrees is square root of 3 over 2 plus I times the sine of 30 degrees is a half, and this gives you the square root of 3 plus I. If you multiply that number by itself 6 times, you won't believe it, but you'll get negative 64. That is one of the 6 answers. Now we're going to let k equal 1. Now we're going to let k equal 1. We're going to do this up until we get 1 less than 6. The 6th root, we let k go up to 5. The 10th root, we go up to k equals 9. 1 less. So now, k is the magic number 1. K is 1. So we get negative 64 to the 6th. One of their 6 answers are 2 times cosine of, you're copying the very last line. If k is 1, then 2 pi times 1 is 2 pi, plus the pi in the front is 3 pi. 3 pi over 6 is half for pi. Cosine of half for pi plus I sine half for pi. Now half for pi is 90 degrees, and for 90 degrees we use triangles. I mean we use the graph. The cosine of 90 degrees is 0. The sine of 90 degrees is 1. So that's 0 and this is 1. So we get 2 times I, or 2i. If you multiply that by itself 6 times, you will get negative 64. Yes, okay. I was thinking you would get 64. You would get negative 64. Okay, now we so those are 2 answers. Those are 2 answers. Let's find the 3rd answer. We just keep doing this. It's rather boring and dry, but it's a lot better than any other techniques out there. Now we let k equal 2. So the 6th root, this is just another way of writing the 6th root. You can raise it to the 1 over 6 power, or you can put the 6th root in front. This is equal to 2 times. Now, so the angle is pi plus 2 pi k over 6. If k is 2, 2 pi times 2 is 4 pi, plus 1 pi is 5 pi. So it's the cosine of 5 pi over 6 plus I times the sine of 5 pi over 6. But we know what 5 pi over 6 is. Pi over 6 is 30, so 5 pi over 6 is 150. So we draw a triangle 150, and then we go from there. If I draw an angle of 150, then this 30 degrees for the reference angle. 1, 2, square root of 3, negative, positive. Okay, so now the cosine of 5 pi over 6 is negative the square root of 3 over 2 times plus I times the sine, which is 1 over 2, and we just get negative square root of 3 plus 1i. You multiply this by itself 6 times, you get negative 64. And you keep doing this for 4 and 5 and 6. I meant to say 4. We just did k equals 2. Do it for k equals 3. Do it for k equals 4. Do it for k equals 5. Don't bother for k equals 6. That's going to be the same as for 0. For k equals 0. Verify that. What 3 pi over 6 or pi over 2. If k is 2, then this will be 4 pi plus the pi in front. That's 5 pi over 6. If k is equal to 3, you get 6 pi plus 1 pi. That's 7 pi over 6. If k is 4, this will be 8 pi plus 1 is 9 pi. 9 pi over 6 is 3 pi over 2. If k is 5, then this will be 10 pi plus 1 pi. That's 11 pi over 6. Now, if k is 6, then 2 pi k will be 12 pi. So basically, you have pi plus 12 pi over 6. Well, that is pi over 6 plus 2 pi. 12 pi over 6 is 2 pi. But with respect to finding trig functions of pi over 6 plus 2 pi, it's the same as just finding sines and cosines, etc. of pi over 6. This is the same as k equals 0. When k equals 7, when k is equal to 7, let's see what we get. 2 pi times 7 will be 14 pi. So you have pi plus 14 pi over 6. You have 15 pi over 6. Okay? Let me erase the top. I'm sorry I'm running out of space. I'm into multiples of taking off multiples of 2 pi. Multiples of 2 pi. Okay. 15 pi over 6 is the same as 12 pi over 6. This here is the same as 12 pi over 6 plus 3 pi over 6. This is a multiple of 2 pi. You could ignore it. 3 pi over 6 is pi over 2. Exactly what you get when k is 1. So you don't need to do 6 nor 7. You don't need to do k equals 8 because they're repeating. They're repeating. Okay, I hope you understood this. It was pretty deep. Good luck with it, folks. Thank you.